Welcome to the fourth lecture of the course, that is on dynamic equation of motion of a two-link manipulator using Newton-Euler approach. So, let us begin. So, this is a two-link planar arm that is shown here with x axis and y axis shown here. The first link is attached here, the second link is attached at here at the tip of the first link, okay, and this is your end effector, okay. F12 is the interaction force between the links, link 1 and link 2. Similarly, there would be F01, that is between the ground and the ground fixed frame and the link 1, okay, and this is your F from external force, that is not considered here, that is considered as 0. Vc2 is the center of mass velocity. So, these are the center of mass locations. So, if I assume links to be homogeneous, so that resides exactly at the center. So, this is the LC1 and LC2 are the distances of center of mass from one end of it, okay. L1 and L2 are the link lengths, okay. Theta 1 and theta 2 are the joint angles and corresponding joint torques are tau 1 and tau 2. M1 and M2 are their masses and I1 and I2 are the moment of inertia about center of mass of those links, okay. So, forming Newton-Euler equation here for the first link first, okay. So, sum of all the external forces on the link should equate to the mass into acceleration part of it. So, that is what it is, very trivial, simple. So, F01 is the force from this direction on this link, F12 is the interaction force between the links, okay, link 1 and link 2, okay, and M1g is the gravitational force on this link. So, sum of all the forces, if it is unbalanced, creates this mass into acceleration, that is Vc1 dot, okay, that is the acceleration. So, and when we bring it to all one side, it should equate to 0. Similarly, the moment balance equation can be N01 that comes from outside, N12 from between the links, okay, and the forces which were there, that will create moment at the center of mass locations. So, F12 into R1C1, so that is this, okay, and similarly F01 which is here from outside, that is from the ground fixed frame to the link 1, F01 cross R0C1. So, that is this distance here, okay, that is the vector here, and all these should now equate to moment of inertia into angular acceleration, and when it is brought to same side, it is equating to 0. So, this is Newton-Euler equation for the link 1. So, note here, inertia tensor is a scalar quantity I1 and I2. Centroid of each link is assumed at its center, okay. Similarly, Newton-Euler equation for link 2 can be written as this. So, it is F12, that is here, there is no external force that acts on it, and M2g is the force due to gravity acting at the center of mass location. So, M2g. So, sum of all the three forces, if it is in motion, it should equate to M2 Vc2 dot, that is mass into acceleration, okay. So, this forms your first equation, and second equation is moment balance equation. Here you have moment coming from here, moment coming from here, this is 0 and this has some interaction moment which is there, okay, that is N12 which is visible here, and the forces will create some moment as well. So, that can be like this. So, F12 into R1C2, so that is the component here, and that is all. So, there is no other moment which is there that should create moment of inertia into omega 2 dot, that is angular acceleration, okay. So, that should now equate to 0. So, this is the pair of equation okay, which is for link 2. So, using these two will try to move ahead and extract the unknowns which are there. Okay. So, for planar system, n I minus 1 I may be written as 0 0 tau 1 transpose. As you know, it is along z direction, that is perpendicular to this plane, x, y and z is perpendicular to this plane. So, that is here. So, 0 0 tau 1. So, tau 1 and tau 2 both are here. So, one of them is here, other one is here for both the links. Okay. Now, let us use these two pairs. So, now eliminating F12, we get this, that is from the equation pair this one. I have extracted F12 and substituted here, or otherwise both are same, and I got to tau 2. I could directly obtain tau 2, and similarly F01 from the first pair of equation, that is this one, F01, and F12 comes from here, that goes here, and F01 which is here. So, all those can be extracted now, and you get to this, that is tau 1 minus tau 2 is equal to whole of this. Okay. So, both tau 1 and tau 2 can now be solved using these two equations, and now I can also obtain C1, this is the mass center location of the first link, C2 is the mass center location for the second link. So, this is quite trivial, that is in frame 1, these are in frame 1. Okay. So, that is why it is so long. Okay. So, C1 and C2 I have used this also when I substituted in the root equations. Okay. And similarly VC1 and VC2 are just derivative of this. C1 dot is VC1, C2 dot is VC2, that can be quickly derived like this. So, substituting all these to this equation and solving for tau 1 and tau 2, we can write the general closed form dynamic equation of motion like this. Okay. So, where this is a vector matrix form, so it is packed in a column format. Okay. Tau 1 and tau 2 will come like this. Generalized inertia matrix, that is 2 cross 2 matrix formed out of the terms containing the angular acceleration, that is theta 1 double dot and theta 2 double dot, both of them comes as a column here. Similarly, centripetal term is again a 2 cross 2 matrix, and it contains all the angular velocity square terms, that is theta 1 dot square and theta 2 dot square. So, that is arranged here, this again is 2 cross 2, and the Coriolis term, that is product of angular velocities terms, they are arranged like this. Okay. And the last term is the gravitational term. Okay. That is the gravitational torque due to gravity, those terms are arranged here. Okay. So, you can express the tau 1 and tau 2 which is extracted out of these two equations, and substituting all these, you can write that in this form. So, doing so, you directly get the terms of generalized inertia matrix like this, I11, I21 and 12 both are same, okay, and I22. Okay. So, what is the significance of this? Let us say you have your link which is like this, first link and the second link. If I freeze this second link over here at an angle theta 2, so whatever is the torque that comes here, it is because of the combined motion of link 1 and 2 together in this configuration. So, that is the first term of your matrix which is here of generalized inertia matrix. So, this is the combined moment of inertia of joint 2 which is immobilized. Okay. It is not moving with respect to link 1. So, that is why this is so big term. Again, the term which is here, this is I22, is very simple. Okay. You just have moment of inertia which was given about mass center location, that is I2, you just have transferred from here to axis of rotation, that is over here, and these two are interaction between the joints, they are the product moment of inertia, and that is given by this. Okay. So, this is the physical significance of having these terms in place. Okay. So, the diagonal matrix are principal moment of inertia and these are product moment of inertia. Okay. So, likewise you can continue if at all there is 3 link. So, this will be link 3 alone, this will be due to link 2 and 3 and this will be due to link 1, 2 and 3 and remaining will be product moment of inertias. Okay. Remaining part. Okay. So, now the centripetal terms are here H11, H21, H22, H12. Okay. All 4 are different, they are here. Coriolis terms are here C11 and C21, okay, that is here, and gravity terms, they are directly here. So, what does this represent? Basically, this is directly the gravitational torque, irrespective of the robot in motion or it is not motion, this term is always there. Even if it is not moving, this is the amount of torque which is to be supplied continuously at the joint. So, this is what we have obtained also while we were doing gravity compensation in robot statics. So, this is exactly the same term. You just put the angular acceleration and velocity term equal to 0 in equation of motion, you get these terms. So, you are remaining with gamma 1 and gamma 2. So, this is the gravity term. So, now let us compare Newton-Euler and Lagrange-Euler formulation. So, what is Lagrange-Euler formulation doing? Okay, it is a multi-body robot seen as a whole. What you did? You basically calculated the Lagrangian for whole of the system together and then you did partial derivatives, applied LE formulation and get to the torque. Okay. So, constraints that are there, that is the internal reaction forces F01, F12. So, that is the reaction forces between the links are automatically eliminated. In fact, they do not do any valuable work. So, that is the reason that gets automatically eliminated. Okay. Closed form symbolic equation of motion is directly obtained without solving them. Okay. Without solving them, you do not have pairs of any equation for each of the link. Solving them together gives you something, but in this case you can directly obtain that. Okay. Best suited for study of dynamic properties and analysis of control scheme. Okay. Whereas in case of Newton-Euler formulation, dynamic equation is written separately for each link or the body. Okay. You saw that just now. Inverse dynamics in real time, equations are evaluated in a numeric and recursive way. So, any approach allows doing recursive formulation also. So, that is the reason they can be done in no time. So, it can be done in recursive way and very faster. Okay. Best for implementation in model based control scheme. So, in model based control scheme, you tend to calculate the torques during runtime of the robot. You directly, for a given trajectory, you keep calculating the torque, feeding it to the robot. Okay. So, you need to do dynamic solution on line. Okay. So, you need to be very fast. So, that is the reason Newton-Euler supports that very easily. So, it is best implementation in model based control scheme and eliminating reaction forces, back substitution of expression, we still get closed form dynamic equation of motion as in case of Euler-Lagrange solution. So, we get to the same result here, but additionally we also get the interaction forces. These interaction forces are very helpful when we try to do any FEM analysis while designing any link, let us say. So, you know the forces and moments from both the side, you know the gravitational forces. So, whole of the link forces are known, internal forces as well as external forces of the link. So, that is the reason while designing the link it becomes very useful. Now, let us see if we can extend the simulation blocks that we have prepared earlier, if it can do the inverse dynamics simulation also. Inverse dynamics basically here I would mean you have a trajectory in hand, corresponding to that you calculate the joint torques using the equation of motion and feed it to the robot and see if it goes in a trajectory which is planned. Okay. So yes, let us continue. So what I am doing, I am using the same simulation model. This time again I will just create the object, importing the simulation model of the two-link manipulator, what we have done earlier. So it is the name of the simulation file, that is two-link planar lecture 4.slx. Import that. It creates the object in the workspace. Okay, this is rigid body tree basically. So now I will insert the polynomial trajectory block. This takes input as time, simulation time, and calculates the trajectory. So these are the waypoints for joint 1, it is 0 to pi by 2. Using cubic polynomial trajectory, you can see the parameters, our method is cubic polynomial. For the second joint, it is 0 to pi by 2 once again. Okay. This is the waveform for the time points 0 to 10. So from 0 to 10 seconds, that is the total simulation time, it will go from 0 to pi by 2, first joint as well as second joint 0 to pi by 2. Velocity boundary condition is 0, 0, it starts with a 0 velocity. So you see it gives me joint rates as well as joint angles. So it is calculating polynomial trajectory as joint angle, joint rate and joint acceleration. Okay. Now I will perform robot inverse dynamics. It takes input for the configuration, that is the joint configuration, that is the joint angle, joint velocity and joint acceleration. It will use equation of motion of this robot. So I will make it take the data of this robot from two-link tree which we have created in the workspace. So joint torque is calculated here, and again I will transfer these joint torques to the joints. So this time the joint should take torque is provided by the input and motion is automatically computed. Okay. Again simulating to physical system data converter. Okay. These are physical values that will go to the joints. Okay. Now I will run this simulation and you see 0 to pi by 2 for both the joints I have fed, and it is moving in a cubic polynomial trajectory, both the joints. So it goes like that. Okay. These angles can be edited, you can try changing that also. 0 to pi by 3 for the first one and 0 to pi by 6 for the second one. Run it once again. It creates a torque profile basically for corresponding to the joint angle profile, and we are feeding it to the robot joints and seeing the motion. So exactly it is following that. Okay. Okay. You can keep on changing for multiple values, 3 pi by 4 and pi by 2. Okay. Again run it. Pi by 4 and second one is pi by 2. Starting and ending time for both of them is 10 seconds. So you see we have done dynamic simulation as well using the two-link manipulator system. So we will complete the dynamics here. We have seen all the algorithms, how to compute the dynamic equation of motion. We have seen how to simulate them. In next module, we will start using them also for our force control algorithms. Okay. That's all. Thanks a lot.